Welcome back to Chemical Kinetics. Today we are looking at the integrated rate law. So a quick recap of what we have done so far. We talked about the differential rate law, which looked something like this. Rate is equal to K, the rate constant, times the concentration of the reactant raised to some power n, where this n is the order with respect to A. And what we learned at that time was that if n is equal to 1, that is if it is a first order reaction, then if you double the initial concentration of A, the rate changes by 2 times, which means rate also doubles. But if the order of the reaction was 2, so if it's a second order reaction, then when you double the concentration of A, the rate changes by 4 times. So the rate quadruples. Which means that our differential rate law was giving us a relationship between the rate and concentration. The integrated rate law, on the other hand, gives us the relationship between concentration and time. So there is a derivation for the integrated rate law which is not required for the AP course, but in class I usually go over it with the kids who are interested, and here I will possibly add the derivation to the end of this video. The equations for the integrated rate laws are given to you on the AP formula sheet. They are not labeled, so it's your job to recognize the 0th, first and second order reaction equations. Now you want to make sure that you understand what the difference is between the two rate laws, integrated and differential. And the answer is nothing. Semantics maybe. They are synonyms in that they are both saying the exact same thing but in different words. The difference comes from your need. You as a chemist, what is it that you're interested in studying today? The dependence of rate on concentration or the dependence of concentration on time? For the first one, you use the differential rate law. For the second one, you use the integrated rate law. They are both interchangeable in that they both do come one from the other. So you can derive the integrated rate law from the differential rate law, and you can go back also. So let's take a quick look at what the AP exam expects us to be able to do. So the first thing it wants you to do is to be able to recognize which equation belongs to which reaction order, 0th, first or second. Second, to be able to read order from a given graph. And the third is to solve equations where you're either solving for concentration or time or rate constant. One subset of solving for time is half-life questions. So we're going to look at all these numerical problems in a second. So step 1, recognizing which equation belongs to which order of reaction. Well, hopefully by now you already know your differential rate law equations as rate is equal to K. So here there is no value for concentration because we think that concentration term is raised to order 0, which means there's no point writing it. First order, second order, reading from the n value or the exponent here. Okay, and then as I said, I will show the derivations to those who are interested, but these are the integrated rate law equations. In lieu of learning how to derive it, you just have to simply memorize. The equations are given to you here on the formula sheet. You should be able to say which equation belongs to which order so that you can use the correct equation for any numerical problem given to you. Okay, so the first thing we are going to learn really is how to read order given a graph. This could be a multiple choice question or it could be a free response question. So let's start first with the differential rate law. You're already familiar with this equation. So if we said rate was on the y-axis, then we are basically saying y is equal to k. There is no variable written for the x-axis. So then a graph for something like this would be on the y-axis, you would write rate. And on the x-axis, you see differential rate law is relating the rate to concentration. So the x-axis would get concentration. Instead of writing the word concentration, I'm just writing A in those square brackets, which is concentration of A. So The shape of this graph would be y value is constant for all values of x. Okay, and from this graph you can read that this is k. For a first order reaction, if this is still y, this is x, so this equation looks like y equals kx, which is your y equals mx equation. And then again, the graph would look like your y-axis would have rate, x-axis has concentration, and if you pardon me, I'll just copy the, okay. So the graph here is y equals kx. So I get a straight line, and in this case, the slope is k. For a second order reaction, this looks like y equals kx square. So that's your quadratic, and we could graph it like this. Okay, so those are the three shapes for the three orders that we have learned. Like I said, on a multiple choice question, you might get these three graphs and the question says, what is the order of this reaction? So you sort of have to know the equation and the graph that each equation generates. Now let's look at the integrated rate law graphs. So picking the equations from the AP formula sheet, if we think that this is y equals mx plus b. So let's relate this equation. So what does that tell me? So this tells me that the y-axis is concentration and the x-axis is time. So let me draw a graph like that. Time, concentration. So the graph is a straight line and the slope is negative. So this graph would look something like this. So the slope is negative k. The y-intercept B is the initial concentration A naught, and AT would be the concentration at any given time. Let's see what happens if we want to draw a graph for a first order reaction. In this case, if we try to relate this equation to your usual y equals mx plus b, then notice that y changes. It is not just concentration. This time y is the ln of concentration. So we'll use that as our axis. So the axis would say ln concentration on the y-axis, and the x-axis is still time. The graph would look like this. The slope is equal to negative k, and in this case the y-intercept is ln concentration initial. So that is your y-intercept. Applying the exact same process to a second order reaction, if we try to find correlation between this and y equals mx plus b, that tells me that y must be 1 over concentration. So this graph looks like x is still time, but y at this time is 1 over concentration. So it is the reciprocal of concentration. And now for the first time we see a graph with a positive slope. So then the straight line looks like this. The slope of this line is k, and the y-intercept here is 1 over initial concentration. So again, take a second, look at these various graphs. It could be a multiple choice question where the three graphs are given to you and you're asked to find the graph that is second order. So it is really important in these kind of questions to very carefully look at the axes. It is always time on the x-axis, so you want to make sure that you're reading the y-axis carefully, and that is always different in the three graphs. It is not a lot to remember because the y-axis always comes from this equation, which, as I said, is already given to you on the formula sheet. And now let's go to the final type of questions, the numerical problems involving integrated rate law. I will take the example of the 0th order reaction, and then the same idea applies to all the other orders as well. So in this case, let's count the number of variables you have. So there is variable 1, 2, 3, 4. So in total, there are 4 things you could solve for, which means that any question must give you 3 of these values and ask you to solve for the 4th. It really is just a simple grade 9 algebra question. So if they ask you to find, let's say the question mark is concentration at time t, then they will have to give you the value of the rate constant, the time, and the initial concentration. If they ask you to find the time it takes to reach a particular concentration, then they will have to give you the concentrations and the rate constant. Or the only other thing now they can ask you to find is, if they said find the rate constant, then be sure that somewhere in the question you're given the value of time and the initial and final concentrations. There really isn't any other kind of question to ask. Before we actually try to solve some of these problems, let's also take a quick look at half-life, because some of those questions will require us to be able to work with half-life as well. Now, half-life is defined as the time required for the concentration to become half of its initial value. You can think of that as that the final concentration is half of the initial concentration, or exactly the same thing but can be said in different words, where you say that the initial concentration is twice the current or the final concentration. A radioactive decay is one of the best known first order processes. So in this case, we measure the change in mass rather than a change in concentration. So when we say that, for example, here, chromium 51 has a half-life of 28 days. What we are saying is that upon day 0, you started with 100 grams. Then in 28 days, only half, 50 grams is left. In another 28 days, you have half of 50, 25 grams left. And then in another 28 days, you have 12.5 grams left. Let us take a moment and figure out formulas for half-life for the 0th, 1st and 2nd order reaction. Now, if you remember, I showed you on the AP formula sheet, they give you one half-life expression, and this expression is for the 1st order only. So as far as the AP exam is concerned, I don't think they would ask you any questions other than half-life of a 1st order reaction. But it really isn't a lot of work, so I'm going to take a moment and show you the half-life expressions for 0th, 1st and 2nd order reaction. That way you can answer any question about half-life in these 3 orders. So let's go. So let's say that A0 is twice AT. Okay, so that's what half-life is, and at this time T is T half. So let's plug these into your equation for the integrated rate law for the 0th order reaction. So then I would write AT, no change, equals minus K, and instead of T I will write T half, and instead of A0 I will write 2AT, which gives me T half is equal to AT over K. This is the half-life expression for a 0th order reaction. For a 1st order reaction, doing the same thing. So I plug these options, so that gives me ln AT is equal to a negative K at time T half plus ln of 2AT. Using the rules for ln, I can say this is, so ln 2 over K is T half. Plugging this in my calculator, I get a number. So this is the half-life expression for a 1st order reaction. And similarly, we can solve for the half-life expression for the 2nd order reaction. So this becomes my half-life expression for a 2nd order reaction. So now let's try to take a look at what the graphs of half-life would look like. So if we made a graph of half-life versus concentration, what would we get in all 3 cases? So comparing this equation to y equals mx plus b, what am I getting? I say y is t half equals 1 over k times x. So the equation is basically y equals mx. So this would have a straight line graph where the slope is 1 over k, and as concentration increases, t half also increases. So this is for your 0th order reaction. For a first order reaction, we see y is equal to a constant. There is no concentration term on this side. So the graph would just be T half stays constant. So as concentration increases or decreases, the half-life does not change. It is a numerical value, and the y-intercept gives you this distance is 0.693 divided by k. So you could solve for the rate constant using this graph as well. For the second order reaction, my relationship of this equation to y equals mx plus b looks like this is y equals m divided by x. So the shape of this graph would look something like this. As concentration increases, half-life decreases. Okay, so that's the salient feature of, or the difference between the half-life graphs. Remember, I said one of the tasks on the AP exam is to be able to read order from a graph. So the shapes of the graphs, so in this case, all three graphs have the exact same y-axis, they have the exact same x-axis. But what is different about them are the shapes. In this case, for a 0th order reaction, you have a positive slope. For first order reaction, the graph is just a horizontal line, and for a second order reaction, you're getting the graph of 1 over x. So we have now looked at three different types of graphs: graphs of half-life versus concentration, graphs of rate versus concentration, and then for the integrated rate law, you always have time on the x-axis, but the y-axis is different in each case. Perfect. Having done this, let's now try to answer some numerical problems of these kinds. All these questions with their complete solutions are posted on the class Brightspace. Make sure you try some of them at least. So let's read the question. A certain first order reaction has a half-life of 20 minutes. How much time is required for the reaction to be 99% complete? In all kinds of questions like these, what you need to do is figure out what is given, what is required, and then find the equation to use from the list of equations given to you on the AP formula sheet. So what they've told me is that the reaction is first order, that is given to me. They have given me the T half as 20 minutes. They are asking me to find the solve for time when the reaction is 99% complete. What does this mean? So if the reaction is completed 99%, so whatever A0 you started with, what is left, since 99% has been used up, is only 1% of your initial value A0. So which means your AT is equal to 0.01 A0. That is the only thing which is implied here. So that they've not given it explicitly, you've got to read the question and make sense of this. Once you've done this, you look at your equation. So you go to your first order rate law and the equation is given to you. So I look at my equation, I say, well, I know I start with something A0. They've given me AT, 0.01 A0. They have given me the time. Have they? No, that is the question marks. I have to find the time. So if I knew K, I could solve for the time required for the reaction to be 99% complete. So again, going back to your grade 9-10 math, you remember that there is never really a time when they can ask you to solve two variables from one equation. This means something else is given to me where I can solve one of these two variables. And what is that? T half is 20 minutes. If you remember, a first order reaction is something where the half-life is constant and the expression for half-life is also given to you on that formula sheet. So then we would say, I know that T half is equal to 0.693 over K. Out of these, T half is given to me, K is unknown. So can I isolate K? Yes, I can. So I can write K is equal to 0.693 over T half. Very good. Let me take this K and sub this in here. And my new equation will become ln AT equals, instead of K, I will write negative 0.693, the negative is coming from here, over T half times the time needed now, plus ln A0. Okay, so this is the equation I'm going to use, and in this equation I'm going to say what is given, what is required. Well, AT is given, T half is given to me as 20 minutes. Time is my question mark, and ln A0 is just A0. If it bothers you right now that, oh, but no value for initial concentration is given to me, please note that this is ln of the concentration and the ln of concentration here. So when I bring this to the other side, the two A naughts will cancel each other out. So let's do that. Let's isolate T in this equation by subbing in the numbers. So I would say ln 0.01 A0 equals minus 0.693 over 20 times T plus ln A0. Isolating for T, I get, I'll first bring it to the left side minus, and then that becomes a division here. This whole thing multiplied by negative 20 over 0.693. And now let me get a calculator and plug this in to solve for T. So I get time T is 132.9 minutes. So that's the solution. Let's try a couple more questions. Let's read the question. It says, for a reaction, the initial concentration is given to me and the first two half-lives are given as 56 minutes and 28 minutes. They are asking me to calculate the value of K, and they're saying minus units, which means they don't care. Don't calculate the units for this reaction, units of the rate constant for this reaction. This is probably one of the most complicated questions you might get. So let's look at how would you try to solve something like this. Well, you know that the first half-life is 56 minutes, and then the second half-life is 28 minutes. So this is where you will have to think for a second and go back to where we talked about half-lives. So on the face of it, it looks like, oh wait, half-life is decreasing as you go on. But wait, we are saying as concentration increases, half-life increases for the zeroth order reaction. As concentration increases, half-life stays constant for a first order reaction, and as concentration increases, half-life decreases for a second order reaction. So let's see what's going on here. Let's say you start with some 100 grams or whatever one concentration of something. Then after the first half-life, you're left with 50. Then after the second half-life, you're left with 25. So this means after 56 minutes, you're left with 50 grams, and after another 28 minutes, you're left with 25 grams. So what's going on? When the concentration was 100, the half-life was 56. When the concentration decreased, as time goes on, concentration is decreasing and half-life is also decreasing. So half-life went down to 28. So this tells you that this is in fact a zeroth order reaction because half-life is directly proportional to concentration. So this has to be figured out before you can answer this question. Go to our equation for a zeroth order half-life as shown here. T half is AT over K, and we know that at half-life AT is actually half of whatever the initial concentration was. So we can write this as T half is equal to A naught over 2K. Again, as always, they are asking you to solve for something, which is calculate the K, that is the unknown, which means they must give you the other things. So they gave me the initial concentration and they told me the first half-life as 56. So let me plug those numbers in here and isolate for K. So I would get K is, this is the first half-life if I'm using the initial concentration 4.2. If I wanted to use the second half-life, I will have to use half of 4.2. So this was 56 and that gives me or I can write that as scientific notation 3 times 10 to the minus 2. They did not want me to find the units in any case. Okay, so this is probably the hardest half-life question you could get. Most of the others would be those where they tell you what the order of the reaction is to begin with, and you don't have to deduce it on your own. Like I say always, I have posted all these problems and their solutions on the class Brightspace. So please take some time and look through that. If there's still questions, please come and see me.